Good afternoon, everybody. Thank you for attending our live presentation of this afternoon. Welcome to the virtual 2020 AOCS Annual Meeting and Expo live stream. My name is Silvana Martini. I'm a professor at Utah State University, and I have the pleasure of introducing Dr. David Pink. He's our first presenter today. Dr. Pink is a senior research professor of physics, as well as an adjunct professor in the food science department at St. Francis Xavier University in Canada. Beginning with research in solid state physics, principally magnetically ordered systems, he moved into modeling and computer simulation of bio and model membranes, and 20 years ago changed his research to the physics of food systems. Since then, he has done research on edible oils and food proteins. He taught most physics courses at St. Francis Xavier University and was on the NSERC Council, the board of the Canada Foundation for Innovation, and the advisory board on Triumph. Dr. Pink will begin this session with a talk entitled Crystal Memory Near Discontinuous Triacylglycerol Phase Transitions, Models, Metastable Regimes, and Critical Points. The presentation will be about 20 minutes long, and after he finishes, we will take only a few questions, and we will take a 5 minutes break. After that break, we will start the second presentation on computing the fractal dimension of aggregates, also by Dr. Pink. After this second presentation, we will take as many questions as you want. We will take questions from the first presentation and the second one. I'm looking forward to this interesting mode of conferencing. And with that, I will turn it over to Dr. Pink for his first presentation, Crystal Memory Near Discontinuous Triacylglycerol Phase Transition, Models, Metastable Regimes, and Critical Points. Thank you, David.
Thank you, Silvana. Crystal memory has been with us for a long time, but while thinking about it in this new mode of presentation, I feel like the world's last astrophysicist, sitting under his radio telescope in some desert somewhere, beaming a talk out to the cosmos, wondering, are they listening there on an exoplanet around Alpha Centauri? Is indeed anyone out there? When Gianfranco Mezzanti told me about crystal memory, I found it fascinating. I found it magical almost. I was tempted to say, surely, how can this be true, Gianfranco? But in fact, when I thought about it, I realized he's absolutely right. It has been extended from describing polymer thermodynamics near phase transitions, and it has been extended to study memory in triacylglycerol systems, tags. What I want to address this afternoon is some little ideas that I had about it. Certainly Alejandro and Marjorie and Gianfranco are equally responsible for all this because they've bought into it. It's what are the physical reasons for crystal memory? What is the processes by which it arises? And here are some nice papers to read, a couple of theses and some papers. Discontinuous phase transitions of single component systems. They exhibit regimes of metastability. Metastability arises not only in supercooling, but also in superheating. And it is this that I want to propose as the basis for crystal memory and tag systems associated with metastable regimes in which components of two equilibrium phases coexist at given temperature and pressure. Now, in order to do some calculations, thermodynamics, statistical mechanics, one needs an energy operator. a Hamiltonian. And I showed to you up there. Um, the At the bottom, I have identified in yellow the key things I want to tell you about. I and J refer to particular molecules. M and N refer to the states of the molecules. So we have pair interactions, the first term there, and single molecule energies. The energies are EM, which you see in yellow, and the states, the mth state possesses a degeneracy, DM. Degeneracy means the number of states possessing that energy. Then these molecules interact via pair interactions, JMN, which you see near the bottom. And finally, there are these P's, which are called projection operators. And they're simply useful mathematical things. A PIM, which you can see there, it says that if we are talking about the ith molecule in its state M, then PIM is equal to 1, and otherwise it is equal to 0. Now, I'm going to first simplify this model because essentially we are looking at a discontinuous phase transition. We really only need two states. I'm not going to defend this statement too much, but really essentially we need two states, a ground state, and I show you some examples of it, A, B, C, D on the right-hand side. These are sort of H-shaped conformers in which either you can have an all trans state in A, or you can have some of these chains are twisted into kinks and trans-gauche isomers and things like this. These are low energy states, and if we sort of put them together, we get an effective ground state. Then there's a high energy excited state, what I call a Y conformer, shown on the right-hand side. And this has a high energy, but also a very high degeneracy. There are many states which approximately have that energy. And now the Hamiltonian function has become simplified. We have lost all this summation over states M and N because there are only two of them now, and this can all be accommodated by this operator sigma. Sigma is equal to 1 if the system is in the ground state, that is, it's a crystal. Sigma equal +1 can be thought of as something pointing up. If the system is in the excited state, that is, if the crystal has melted, then sigma is equal to -1, and one can think of it as pointing down. This looks like the Hamiltonian function for something called the Ising model, which I put down here. It's a model of magnetism. And this function H on the right-hand side, this is an effective field. At low energies, at low temperatures, T is 0 essentially. And so the term in the degeneracies can be ignored and H points up. So it drives sigma to point up, and therefore the system it's a crystal. At very high temperatures, the second term in H dominates, and it now points down because there's a negative sign, and this drives the sigmas to point down. That is, the crystal has become melted. So this describes a nice discontinuous or phase transition. Then we can assume that only nearest neighbor interactions are important, so this simplifies things even further. This is a perfectly good assumption because if we're dealing only with dispersion interactions, these fall off like 1 over r to the 6th. And so nearest neighbors is quite adequate. But if we're dealing with electrostatics, then we cannot easily accommodate this assumption. And why should there be electrostatics? Well, they are, of course, because the glycerol core of these molecules contain what are called partial charges. But making this assumption, we've got a nice simple Hamiltonian, as simple as we can make it, an Ising type model. What does the thermodynamics of this model look like? Well, if we ignore H, okay, so H is at the bottom down there, near the bottom. If we just ignore it, then we have the Ising model in zero field, and we get what is shown in figure A. In green is shown the equilibrium solutions at low temperatures on to the left. The sigma points up to +1. That's the ground state. That's the crystal. As we heat up the system, we get a phase transition, a continuous phase transition at a critical temperature Tc. This is continuous. That is, you see it goes to zero and connects up with the melted state as the temperature rises. Now, if, however, we include H in here, then we get a much more interesting possibility that I will show here. We've identified a temperature T star, and T star is when this field H becomes zero. Now remember, if H is at low temperatures, it points up, so that the sigma is +1, it shows there at low temperatures. If T star is less than Tc, then one gets this discontinuous jump in from the low temperature state with sigma is +1, the crystal, to the high temperature state in which the crystal has melted. And there is the discontinuous phase transition at T star. However, there's still another interesting one. If Tc lies below T star, then you can see in part C that the equilibrium state in green just shows no phase transition at all, just a phase change in which the crystal gradually melts, comes apart, turns into a liquid. Okay, so now I'm going to make a mean field approximation, and what this does is to approximate the interaction term. And so on the right-hand side there, that's B again, it's just a bit bigger. I've shown you where the metastable state is in red. This approximation simplifies the interaction term, but does not change T star. What it does is to change Tc. T star remains the same, the temperature at which the phase transition occurs. And if I simplify things further in a pretty trivial way, this is not an important point, then I can solve for this average value of sigma in terms of H and temperature T. At low temperatures, sigma will be about 1. At high temperatures, sigma will be about -1. Okay? And this comes out from this equation. Okay, let me just give a rough description of the experiments that Gianfranco has done for this to measure stuff. It's shown here in a nice way that Gianfranco sent me. Do I know anything about this? Well, I can follow the words, let's put it that way. There are two stages. A tempering stage in which everything is brought to the state that one wants, and a testing stage that's shown by the blue arrow at the bottom, in which one tests to see if it came out the way one wanted. The tempering has 4 parts in it, A, B, C, D, shown on the right-hand side. These are the 4 steps that one takes in order to bring the crystal eventually to the state one wants. One tests it, that's the blue region, by first cooling it into the solid state. One keeps it there for a while, and then one melts it. That's the one labeled number 6. They are heated, and one looks at the characteristics of the phase transition to see what one had. And one finds that, in fact, this procedure of tempering creates the beta polymorphic form. Okay, theory, results, and discussion. The superheated regime, that is the one in red there, you see in the picture B, can be accessed by heating, not slowly, because you don't want the thing to drop down into equilibrium right away. You're trying to keep it in this non-equilibrium state, and it will be composed of components from the low temperature state, that is crystallites, of solid fats in a beta polymorphic form and in a sea of liquid oil. And it is this that we're proposing is the reason for crystal memory, because the crystals, the system in the superheated state will remember, it will have examples of where it came from. And so these solid fat crystals in beta polymorphic form will act as nucleation centers for if we cool the system fairly quickly now. So if we cool the system, the what were the melted lipid molecules, melted tags, will coalesce onto these crystallites in the beta polymorphic form and simply recover the beta polymorph crystal. Now, one should try to get some predictions because a theory is useless if it only explains things, because you've got to try to invalidate it somehow. And the easiest way I could think of was by changing the length of the hydrocarbon chains. And there are two limits. Physicists would say L goes to infinity, which we can't do, or L goes to zero, which won't work. But it means L becomes very long or L becomes much shorter. So as L increases, all right, we know, I mean, I can prove that if you change the parameters of this model, TC changes very much faster than does T star. So if you look there on the right-hand side in B, if we make the chains very long, TC will take off towards the right-hand end, leaving T star in the dust, and the transition enthalpy will increase. It will increase for two reasons. The first reason, of course, is the chains are longer, and therefore there's more energy, but it will also increase because as TC moves away from T star, the transition becomes much harder. That dashed vertical line becomes longer. And so there's more energy than simply what is accounted for by the longer hydrocarbon chain. On the other hand, as if we can shorten the hydrocarbon chains and L decreases, then again, remember, TC moves much faster than does T star as we change this. So TC will start decreasing and approaching T star. Eventually, it will hit T star. And at this point, there will be no discontinuous phase transition. This vertical dashed line will have gone to zero. We will have a continuous phase transition. And in this case, the crystal memory effects should go to zero. There should be no crystal memory when TC hits T star. And in fact, as TC passes T star, and we're now in picture C there, then there's no phase transition at all, discontinuous or continuous, just a phase change. Everything melts slightly. There are no metastable states. There's no superheating or anything. There will be no crystal memory. So by changing the length of the hydrocarbon chains, we can reduce crystal memory and in fact, cause it to disappear completely. This is shown at the bottom there on the right-hand side. Okay? This would be a very broad transition with very small fluctuations. And certainly in the absence of a superheated metastable state, there should be no crystal memory observed. Now, there are other experiments that one does, the relationship between the metastable regime and time temperature data. On the right-hand side, I've shown you the case where there is the discontinuous transition, and I've blown it up here. See, there are three temperatures, T1, T2, T3. They are equally spaced. One is near the end of the metastable region. The other is near the phase transition vertical dashed line. And I want to calculate the lifetimes for these metastable states. And the only way I could think of doing it was to use a modified Vogel-Fulcher-Taman equation, which I show you down there. It's modified trivially by adding a tau zero on the left-hand side. And the reason I did this was to get the right limits. You see, as the temperature Tn goes to T star, then we must find that tau, the lifetime, goes to infinity because we are moving towards an equilibrium state. Now, this will come out whether we have a tau zero on the left-hand side or not. But also, if the temperature Tn goes to infinity, then we certainly want the lifetime to be zero, and that's why tau zero is there. Okay, so we can now plot lifetime temperature relationship for these three lifetimes, tau 1 to tau 3, and I show it to you in the plot on the right-hand side. Just look at, there are two regions. This solid line with two bends in it, this is the locus of the temperature tau equation, relation obtained from the VFT equation. Think about the following. If we're in region 1, okay, that's the lower left, then at a given temperature, we can keep something in region 1 and simply call it the holding time. And if we hold it there, then we can, as long as we don't go to the solid line separating regions 1 and 2, then we can reduce the temperature and we will recover the original crystal that we started with. That is, crystal memory will be recovered if we are in region 1. But if we're in region 2, we're outside the temperature tau line, and we will not be able to return to the crystal that we started with. In fact, everything is likely to be melted there, and so there's no reason for the molecules to remember which solid they came from. So region 1, we will see the crystal memory. Region 2, we will not. And this is similar to the results, the experimental results reported by Wang for her thesis, figure 418. She shows holding time boundaries. I'm saying that the holding time boundaries that she has found is the temperature tau line that I've drawn there. So we can have conclusions. We have modeled crystal memory as a temperature decrease from a metastable regime where we have crystallites that remember where they came from because they haven't changed their structure. We employed a model that has been used to look at Raman data in the transition region. We used a modified VFT equation to compute the time temperature relationships, and we have tried to make predictions concerning changes in the phase transitions as we change the hydrocarbon chain length of the molecules. Finally, thanks to the people who paid for it. They're all listed there. And also to all of you, if you are existing out there on an exoplanet around Alpha Centauri, you will hear this talk in approximately 4 years. So thank you for your attention.
Thank you, David, for an exciting presentation. It was very interesting. We do have 2 questions that we might want to answer now. The first question is, wouldn't the conformer E have the highest entropy due to its highest degeneracy, and thus be the most stable one?
And the answer is the statement is correct. It has the highest entropy, but the answer is no, it will not be the most stable because stability depends on the temperature. And the fact that phase transitions exist means that even though there are low energy states with low entropies. Nonetheless, they win because the high entropy state becomes less and less probable as temperature goes down. Is that clear enough? You can have you can have another question later on if that's not clear enough.
I was going, yeah, definitely. We can follow up after the second presentation.
Absolutely.
Let's see the second question that we have.
Yeah.
And the second question says, did I misunderstand? If T star is greater than TC, we do not have a discontinuous first order phase transition anymore.
That is correct. There's no phase transition at all if T star is greater than TC, there is no phase transition. There's a gradual phase change.
And that would be the case of short of fatty
acids. It have to be short chains, yes. If one can make such a system that you can make a crystal of sufficiently short chains, then there will be no phase transition.
Great. Well, thank you very much, everybody, for the questions. Thank you, Dr. Pink, for your presentation. We're going to take then a brief
5 minutes.
5-minute break. Yeah. And we will be back in 5 minutes, about 1:33.
Right.
2:33 Central Time. Sorry.
That's right. I'll be back.
Okay. Bye-bye.
Yeah.
Okay, Dr. Pink, whenever
Yes.
you're ready, we can start with the next presentation.
Yes, right.
Thank you.
Okay, I will. Silvana, let me just ask you, I can roll now, can I?
Yes, you can. Go ahead.
Yeah, I'm just trying to get back here.
We can see your slides and everything.
Okay, I have just lost control of them. Huh. Hang on. I wonder. I wonder why. Hmm.
So you can try hitting escape and relaunching the
Yes,
slideshow.
that's right. I
Let's
tried
try
it.
that.
I tried it and it didn't work.
Okay.
Should I stop share and try to get it back?
We can try that. Yeah, if you want to
Yeah.
stop sharing your screen.
Yeah. Let me see
Then
now.
see about closing that and reopening it, and we'll see if we can get it back up.
Yeah. Okay, I'm just looking to see where to close it. I could try exit full screen. That's funny. I wonder why. Okay, good. Good. Got it back. So we can start sharing again. Shall I hit something?
Let's share the screen again, and hopefully this time
Yes.
it will behave.
Yeah, I'm just looking for my share. Oh yeah. Share
Move your
screen.
cursor to the bottom, and you'll see.
Yeah. Yeah. Yes. Share. Right. Okay, so now I try and get it back.
And just so you know, this screen.
Yep.
Oh, there you go. Now it's shared.
Got it there. And now from the beginning. Okay. All right, good. So what is this about? Many studies in food science have been concerned with computing the fractal dimension of aggregates, and these have been related to physical properties. For example, in systems of edible oils and renneted milks, one has listed fractal dimensions in terms of aggregates of primary particles. Now, questions arise. To what end are these studies and evaluations carried out? What I mean is it useful? Is it useful? And excuse me, let me connect my battery, which I thought had been all nicely charged. Okay, is it useful to do all these calculations and measurements and so on? I mean, for example, if you were chewing on a fractal, would you enjoy it more than if you're chewing on some stodgy, solid, three-dimensional substance? Or are fractal foods more digestible? I think this would be an amusing PhD study at a university that I can't think of right now, but nonetheless, enzyme access to structures. There are, however, I'm not going to talk about that today. There are more interesting things because I think one thing that fractal dimensionists have not really thought about are questions of shape differences and polydispersity. And that's where I want to get to by the end of this talk. There's also the question is whether fractal dimensions can tell us about the kinetic processes, that's the dynamics, which resulted in the aggregates exhibiting a certain fractal dimension. And this is another question people have asked me. Okay, how do we calculate fractal dimensions of aggregates? And I must say that I'm partial to this method. There's another method, the box counting method, but I like this method. really appeals to me like. It is essentially the absolute value squared of what's called the structure function. And it's related to the structure factor, which one can measure in a way from photon or neutron scattering processes. It depends upon a vector Q, the scattering vector. The magnitude of Q is shown there, about 2 lines down in the second paragraph. It is a well-known relation. S of Q, with Q being not a vector, is an average over all possible vectors Q, all of the same size. Now, if the photons or neutrons scattering from the fractal structure are identical, the objects that are making up the fractal, if they're all identical, and if the structure possesses a fractal dimension d, then we know that S of Q is proportional to Q to the minus d. Okay? And this has been the approach traditionally used to identify fractal dimensions, fractal structures in scattering experiments. However, I want to show you down the road that this is not quite true. First of all, let me show you what typical ultra-small angle X-ray scattering data uses. My colleague, Fernanda Peronel, has collected very nice data. The advanced photon source and argon, and it can be analyzed by the unified fit theory, which is shown on the left-hand side. There's a fit to data there. There's a nice red curve going through data points. There are, in that diagram, one nice constant slope line, one that says surface fractal dimension. And that tells you the surface characteristics of the primary objects which have aggregated and are making up this fractal structure. If you go further to the left and find other nice straight lines, and there's not one there, Hamuda's theory can enable one to discover what is the general shape of the objects which are giving rise to the fractal. So, for example, if S is an integer in Hamuda's theory, and of course S does not come out to be an integer in real life. But if one, for example, finds that S is equal to 1, then one concludes that the objects which are making up this, which are aggregated to make up this fractal structure, they are essentially like long cylinders, one dimension. If S is equal to 2, then the objects which are aggregating are like flat disks or two-dimensional structures. S can also be 0, and one has to be careful here, because if you know that you have spherical objects, they would give rise to a value of S equals 0. But if the converse is not true. If you find S equals 0, it does not necessarily mean that the objects are spherical. It might only mean that you are sufficiently far to the left on the Q scale that you have come really to asymptotia. I want to show you one useful application that Dr. Peronel and has found. I promised her that I would not say what is blue stuff and red stuff, though I understand that she revealed them this morning, not perhaps calling them by these names. You can see there that there are two pretty well linear regions for almost a whole decade of Q down on the left-hand side, one with fractal dimension d equals 2.1, the other with fractal dimension 2.3. And these numbers, they may seem close, but in fact they're not. They're well outside the error bars of the data. So one says that down there in these two substances, blue stuff and red stuff, that the structures are slightly different. Okay, one is slightly more dense than the other. Although the blue stuff and red stuff are made from the same substances, they are being made in different ways and have given rise to these different slopes. One can also say how big they are, because between these two vertical blue arrows, one looks at the range of Q, one uses this rough relationship L equals 2 pi over Q, where L is the linear dimensions of the fractal structures, and one finds that in that region there are objects that range in size from 5 to 20 microns. And Fernanda and I have written a paper about this, and it's quite interesting. Whether it will be rejected or not, I do not know. Now, do shapes matter? The shapes of the primary particles, that is, the particles that are making up this fractal structure. Does it matter what shapes they are? And the answer is no, it does not. Everything that one knows about fractal aggregates, the shapes of them do not matter, as long as all the shapes are the same. For example, if you are causing long cylinders, as shown in the top bit of data there on the right-hand side, long cylinders, all the same size, then you would get the same fractal dimension if you are using the same process as if you are causing flat disks shown at the bottom to aggregate. You can see the aspect ratio is 20 for the long cylinders, whereas it's 1/20 for the flat disks. In the middle, there's one with an aspect ratio of 1. All of these aggregate, if the aggregation process is the same, they will all give rise to the same fractal dimension. And I want you to notice the black line is the structure factor, the structure function actually. I will show you some more structure functions in a minute. There you can see that at very low Q on the left-hand side, there's this characteristic decrease in this Guinea region. On the right-hand side, there are these oscillations, little bumps they're called there by these authors. And in the middle, there's a straight line, and all of them show the same slope of approximately -2. Can we deduce the kind of aggregation by knowing what D is? And the answer is no. We have to consider the system, and here is why. Here are rods, okay, little cylinders aggregating. They're only allowed to aggregate at their ends, as shown in A. If only 2 or fewer rods can stick to each other by their ends, then we come out with a fractal dimension of D equals 1, shown in C. That's the cylinders there. There's no other fractal dimension. And you can see that, in fact, the curve, the figure C, looks pretty well like what Rothenbühler and his colleagues show in the upper right-hand side picture. You see the Guinea decrease at low Q, you see the oscillations at high Q, and you see the straight line giving the fractal dimension in the middle. If, however, 3 or fewer rods can stick together, as shown in A at the top, then you will see D equals 2, indicating that effectively branching is taking place. These images that I show you there are from diffusion limited cluster aggregation, and they form aggregates analogous to swollen, randomly branched polymers. Okay, and you can see that in D. Images of what you see in that case are shown in part B. Now, if you knew that D was equal to 2, could you say whether what you had aggregating? Could you say that they are looking like swollen, randomly branched polymers? Not really. And that's the reason for my saying that just by knowing what the value d is, can we say anything about the kinetics of what brought these together, or the details of what is aggregating? And the answer is no. We really must consider the whole system. Okay, so let's come to the last part, polydispersity. And that's really important because most things really are polydisperse. And there are two papers that I can suggest to you. Bushel and Amal is a nice paper. The one I want to talk about is Martin's, because that really has a very pretty mathematical description of how do you characterize polydispersity. So let's assume that we have an aggregation of polydispersed particles with a distribution number. That is the fraction of the particles which possess mass m. Okay, and I'm going to assume, or rather, Martin assumes that this number, the number distribution P of m, is a power law. It goes like m to the minus tau. This is a perfectly reasonable assumption. Then they find not now that the structure function S of q goes like q to the minus d, where d is a fractal dimension, it goes like q to the minus gamma, where gamma is equal to the fractal dimension times a multiplicative factor that depends upon tau, called the polydispersity exponent. Now you might say, surely this is just a matter of words, isn't it? I mean, whether you called gamma a fractal dimension rather than d, so what? I mean, it's a number that shows how S depends upon Q. And this is certainly true. But nonetheless, think about this. Suppose you find a value for the dependence of S upon Q. Is what you have found telling you, giving you a correct picture? Suppose you find that gamma is really quite small. Do you have a one-dimensional system, or do you have a highly polydispersed system? And the difference is not trivial at all. And I'm going to show you in a minute what I mean. What Martin came up with, that if tau is less than 2, then gamma will always come out to be d. But that if tau lies between 2 and 3, then gamma decreases linearly from d to 0. So you can see that if you have a value of gamma, let's say 1.5, do you have some strange DLCA aggregation, or do you have a very polydispersed system? And this is not at all trivial and needs to be thought about. So can we calculate tau if we know the polydispersity of the particle distribution? The answer is yes, because if we know how this number P of m depends upon m, this will give us tau immediately and will enable us to calculate gamma, which we can then compare to measurements carried out in a lab. Okay, so there's one more paper that I would suggest to you that's really also very nice, in which people did a computer simulation. Eggersdorfer and Pratsinis did a computer simulation of aggregation of polydispersed spheres. They're not all the same size. They're log normally distributed with a standard deviation of between 1 and 3. 1 means that they are monodispersed. 3 means they are really quite polydispersed. And here is what they look like. On the left-hand side, we have sigma, the geometric standard deviation, equals 1. In this case, gamma is equal to d, and it is correct. This is diffusion limited cluster aggregation. The number 1.79 is correct. As the systems, as the spheres become more and more polydispersed, you can see gamma decreases. They have called it D, but in fact it is really gamma from Martin's paper. And as it becomes more and more polydispersed, gamma goes down to 1.48. Now, if one came up with a result of, say, 1.5, one would wonder, is this the fractal dimension of a monodispersed system, or is it the gamma of a polydispersed system? And really, one has to sort this out. One can't just go around claiming one value of fractal dimension simply because one does not want to bother. Think about polydispersity. Look at how much that gamma reduced. It went down to 1.5 once you get very polydispersed. So here's how we've done a little calculation. There is Martin's diagram on the right-hand side. Gamma is equal to d into 3 minus tau. If we take d equal 1.8, that's what we found there on the other picture, Eggersdorfer's picture. D is 1.79, 1.8 is a much more convenient one to take. And if gamma is 1.5, then we find that tau is 2.17, which is, you can see it's sort of 1/6 of the way between 2 and 3. So what are the conclusions here? I like calculating structure function. I'm partial to it. It's a happy thing to calculate. It's straightforward. You can get confocal pictures, for example, of distributions of particles and actually calculate the structure function from that if your pictures are big enough. But it has to be confocal because you have to know where everything is. That's the difficulty with box counting. You have a two-dimensional picture of a three-dimensional structure. I agree you can use box counting if you have a confocal image. If aggregating particles are identical, does the shape of the primary particles matter in getting a fractal dimension? And the answer is no. But is this true even if the system is polydispersed? And I won't spoil your fun at the bar tonight. Some of you can argue either side of this. Does, if all the particles have the same shape, is polydispersity important? The third one is, does polydispersity matter? It sure does. It can give rise to significant insecurities in your interpretations. And of course, this would lead to a very good comment from a referee, have the authors considered polydispersity? And finally, can fractal dimensions tell us about kinetic processes? And the answer is not really. Don't put your reputation on the line, okay? For this one, you can get similar fractal dimensions from quite different systems. So thanks to the funders of this work, the universities, thank you all for your attention. And while I was talking, a note came in. It's a bit strange. It says, thank you for your quite superficial talk. We enjoyed it. We had some good laughs. There is one thing that you had wrong. We are sitting in a stable orbit, electromagnetically masked. We did not come from Alpha Centauri. We are in fact from Epsilon Eridani. And there's a signature at the bottom, which is undecipherable. Thank you very much for listening.
Thank you, Dr. Pink. Very interesting. I always struggle with fractal dimension myself, so I learned quite a bit. Thank you very much. And you'll probably get a few emails from me after this trying to help me understand fractal dimension.
I can give you the talk. You can just get the talk.
But we do have a few questions from the audience.
Sure.
If you're ready, I'm going to start with the first one. It says, how do you feel about the fact that fractal scaling in nature is only observed for very limited range of magnifications, maybe 2 decades?
Yes, one naturally feels insecure with that. And in fact, 2 decades is not very big. So I feel just as insecure as the questioner does. I think one has to be very self-critical in this. And 2 decades is small. I agree. Some parts of nature simply do not collaborate with us on this. We have found that we can get fractals from quite small systems, but generally we get more than 2 decades. Be very suspicious about attaching fractal dimensions to 2-decade data.
Okay, thank you.
Mm.
Next question says, when one throws X-rays or neutrons to a sample, are you probing the structure within the clusters or blobs that make up the network, or the fractality of the distribution of objects in space?
If it's single particle scattering, then you're essentially measuring S of Q. So, and the neutrons are scattering from the nucleus. The photons are scattering from the electron clouds. These are pretty small structures. You will not see a fractal dimension emerging from those. Just tell me the question again. I'm not sure if I appreciated it properly. Do you mind reading it again, Silvana?
Of course, no problem. It says, when one throws X-rays or neutrons into a sample, are you probing the structure within the clusters or blobs that make up the network, or the fractality of the distribution of objects in space?
You're probing where the things are. If it's a single particle scattering, and you have to be careful on that, then the neutrons are scattering from the individual objects, whatever they are. And the fractality emerges from the total scattering S of Q. So, but it is single nucleus scattering. So you're not directly probing the fractal dimension, you're probing the relative positions of the small objects making up the aggregate. Is that sufficiently unambiguous? I hope it is.
I think so. And again, we can always follow up with other questions.
Absolutely. Absolutely.
We'll move on to the next questions.
Mm-hmm.
Wouldn't you expect most of our complex systems to display multifractality? What would be the implications for your theoretical analysis? Do you want me to read that again?
No, I understood it. Yeah, and the answer is yes. I would expect multifractality. I'm not sure how multifractality would exhibit itself in the neutron scattering. Give me 5 seconds to think. There's no question. One would expect multifractals. It could be that you have symmetries there which do not come out, which do not emerge from simply looking at a structure function. Okay, so, I mean, if you have fractal structures on different scales, that's okay. These will be separated. But if the scales are very similar, the length scales, then you'll have problems, I think, in, interpreting the data. If the scales are very, very different, then you'll have simply different regions of Q space, which will identify, these linear parts. And there's a very nice paper by, I think, Schaefer, in which they show 5, 6, 7 different regions, all with different linear slopes that are about approximately a decade wide. And there are different fractal structures on different length scales. Okay, so that's the best I can think of now.
Thank you. That's very good. We have one more question. It says, Dr. Ping, you said fractal dimension does not depend on shape.
Yes.
shape would affect macroscopic structure and rheology, wouldn't fractal dimension be also affected by shape then?
Oh, that's a nice question. Yes, shape. Now, don't forget, the fractal dimension is something that is defined for an infinitely large structure. That's the first thing. And if you imagine stuff aggregating, and you imagine standing very far away from it, so as you can see the entire structure, then all the things that go to make it up look like points. And if that's so, then one might expect that all the physics of such a structure would be the same, whether they're needles or discs or something. Now, the viscosity, for example, this viscosity will appear from out of local interactions, I would think. That is, a fractal made up of different shapes in some medium. The viscosity will depend upon the shapes, but this emerges from the local interactions on a spatial scale the same size as the shapes of the fundamental particles. You cannot deduce fractal dimension from these local length scales. And so if you have two things which appear to have the same fractal dimension, but it turns out that they have different shapes, I would expect then that the viscosity would be different. Moving through the same fluid, these two objects would be different because the interactions are local. That is, a liquid oil scattering off these primary particles that are making up the fractal, then you would expect quite different results. So the viscous behavior would be quite different, but this depends upon the shape of the primary particles and not upon the fractal dimensions, because the interactions there are local. And so, yeah, same fractal dimension structures can well have different flowing characteristics. Does that answer your question, I wonder? You also should have a subsidiary question if you'd like. But it's the difference between very large scale characteristics and very small scale characteristics. And they don't necessarily mean the same thing physically. The small scale characteristics will determine how the thing moves through a fluid. The large scale characteristics will give the fractal dimension. So same fractal dimension can have different viscosity effects.
Thank you. I think, that answers the question.
Mm-hmm.
We have a few more questions. Is that okay with continue? If we continue with a couple more?
Fine with me. I'm just going to have a drink. Yeah, but go ahead.
Okay, the next question says, you talked about the effect of polydispersity on DLCA.
Yes.
Can you comment how polydispersity would affect fractal dimension for reaction limited cluster aggregation, RLCA?
Sure. I don't think there'll be sure. Okay, RLCA, suppose we have DLCA, things are aggregating and they are interacting with a finite size interaction energy. Then you can, as time goes by, these things can rearrange themselves, relax into a more dense structure, and the fractal dimension can go up. We have found that from our own simulations. And this is what we've called reaction limited cluster aggregation, RLCA. So we would have, in this case, DLCA, and then as time goes by, RLCA takes over. If we have polydispersity, then it would just be relaxing more. So as you increase the polydispersity, what will happen? Just imagine, do you remember that picture from Eggersdorfer's paper, picture labeled C for the very polydispersed systems? Just imagine this relaxing a bit. So one might expect that the value of gamma would be higher than 1.48. So everything would sort of move up. The values of gamma would just move up. Would gamma ever get reduced to 1.5, 1.48, as the DLC result did? I don't know. We'd have to actually check it, I think. So I think Eggersdorfer's paper, his DLC simulations, have probably assumed that as soon as these spheres touch, they stick. In this case, you would not get any further relaxation because they can't separate to relax. And so you would never see RLCA there. But if they're finite and they will relax, I'm not sure whether eventually RLCA would approach 1.48 the way his DLC simulations did. But the gamma would simply go up a bit from what, go by 0.2 or something from what Eggersdorfer showed. It was much easier, I think, for him just to do the simulation with an infinite binding energy of the spheres rather than to look at a finite. He would not know how long he'd have to wait and things like this. Okay.
Okay, thank you. So next question says, in your opinion, what would be the best method to determine fractal dimension?
Well, I said I'm biased, man. I like the structure function. It enables you. Well, what does it enable you to do? I'm just biased. Structure function is related directly to the structure factor, which you get out of scattering. That's why I like it. But let's see, is there other advantage than box counting method? Box counting method will give you the fractal dimension, but so it's just my bias. It's just, feeling. Maybe it's because I like algebra, so it's just my hang-ups. That's all it is, I think. Physicists will probably say structure function is related immediately to the absolute value squared of the state function, which is bringing about the scattering of these particles. Yeah, I agree with that. Can I select out certain objects in box counting? Yeah. I mean, the thing is, I just distrust box counting. Have I made the box big enough? Things like that. Whereas with the structure function, I take what I see, man, and I put everything into the calculation.
Great.
Yeah.
Thank you.
Yeah.
And we have one last question.
Of course. Yeah.
One last one. It says, how do you differentiate between polydispersity effects and multifractality?
Oh, I don't know. I'm sorry. Let me think. Well, with multifractality, with a polydispersed system, you see an effective fractal dimension, gamma, right? I mean, you can think about it like that. So you've got this number, gamma. With multifractality, I don't think you would necessarily see, you would not necessarily see a linear region. So if you see a nice linear slope, then you probably just have one type of fractal, and you have S depending on Q to the minus gamma. If you are happy that you don't have polydispersity, then you put gamma equals D. But if you come up with a strange value of gamma, that some people do, 1.2, 1.4, then you just got to be careful. So I think this is the way I would distinguish between them. If I can see a nice straight line, I'll assume in that region I have one fractal dimension, one type of structure. If I cannot identify such a nice linear region, then, well, I'm up a creek without a paddle, right? I mean, that's what it amounts to. Is that okay with you? I think to be paranoid about do I have polydispersity is easier. It's an easier paranoia than multifractality. So, okay.
Okay, great. Thank you very much. That was our last question.
Mm-hmm.
You're all welcome to email Dr. Pink for more questions if you have.
Mm-hmm.
And with that, we thank you all again for being here, and especially to Dr. Pink for giving this live presentation.
Mm-hmm.
And hopefully we'll see you throughout the week through the other sessions and presentations. And with that, we conclude this live stream.
Thank you very much, Silvana, for doing the whole thing so well. And thanks also to the AOCS organizers. I meant to thank you all, and you've done a terrific job with organizing all this at pretty short notice. So well done to you.
Thank you very much.